In the previous video, we've seen that in insulators, there exists an energy gap between occupied electron states and unoccupied electron states. It takes so much energy to get an electron up into the energy state where it can move around the crystal freely that these materials end up not being very good conductors of electricity. In the valence band, the electrons are not free to move around because the available states are all completely occupied. And in the conduction band, we have almost zero electrons to move around to start with. Now, in a metal, it's a different story. There's really no difference between the conduction and valence band of a metal. It just so happens that in a metal, there are a lot of unoccupied states adjacent to those that are occupied. This happens because the elements of a metal crystal, like gold or silver, just happen to have the correct interatomic spacing to make an easy environment for the electrons to migrate around the crystal. So you don't have to give the electrons much energy at all in order for them to find an empty energy level to get to. But all the properties of insulators still generally apply to metals. As you heat up a metal, generally the electrical conductivity will increase because more electrons can be thermally excited from occupied states into unoccupied states. Metals are not transparent, though, because when a photon of light hits a piece of metal, the energy in the light can easily be transferred to electrons in the metal. Metals are then reflective because the energy in an excited electron can then be re-released in the form of light. Inside the metal, it's as if the bottle is half full of water and the water represents electrons. Applying just a little bit of voltage to the piece of metal causes a huge flow of electrons inside the metal. This means that metals have a high electrical conductivity. Let's now imagine applying a voltage to a solid block of silicon or germanium. Imagine a situation where you have a battery with voltage V attached to a block of material with a length d and surface area A. A current I will flow through the material. Current is measured in amperes, and current density J is measured in amperes per unit area. How much current actually flows, of course, depends on the conductivity, sigma, of the material and the applied voltage. The material of the block has a certain conductivity, sigma. Conductivity is the inverse of resistivity, rho. Now let's talk about the conductivity of the material. What are all the things that influence the conductivity of a material? Well, the charge certainly plays a role. Q sub E is just the charge of an electron, or a hole, 1.6 times 10 to the power minus 19 coulombs. It's just a constant. Naturally, the number or concentration of electrons in the conduction band N, or the number of holes in the valence band P, play a role too. So silicon, for example, has only something like 10 to the power 10 electrons in its conduction band at room temperature, and the same number of holes in its valence band. So if that number were higher, the conductivity of silicon would then go up. This is very similar to the equation I showed you before with the bolts of lightning. The number of charge carriers available is directly proportional to the current. The mobility also makes a difference. How easy it is for the electrons to move through a material. If it's hard for the electrons to move, that can be explained by scattering, just as in the case of a bolt of lightning. Electrons move for a while towards the positive terminal of the battery. They hit some other electron and start moving again in maybe a slightly different direction. So any one electron will follow a somewhat chaotic path through the crystal. The easier it is for electrons to move, the higher the electron mobility, which is the Greek letter mu with a subscript E for electrons and a subscript H, because we have holes in the valence band conducting electricity too. In a normal piece of silicon, at thermal equilibrium, the number of electrons in the conduction band is equal to the number of holes in the valence band. It's just that it's easier for the electrons to move than it is for the holes. If we look down here in the table of material properties for the two materials, silicon and germanium, you'll notice that for silicon, it has quite a high electrical resistivity compared to germanium. Germanium still doesn't really conduct electricity very well, but it's certainly more of a conductor than silicon is, isn't it? It's a lot easier for the electrons to be promoted at room temperature into the conduction band for germanium than it is in silicon. Now check out these values for mobility. It's a lot easier for electrons in the conduction band to move through germanium than in silicon, but it's only a factor of 2 or so. It's not a huge difference. Now notice also, in silicon, the hole mobility is lower than the electron mobility is. It's more difficult for holes to move through the crystal than it is for electrons. That's because when we start talking about holes moving through the lattice, it's all these valence electrons that are reorganizing themselves around the hole, bubbling around, and all that reorganization is more difficult than it is for just a single electron in the conduction band to move around a crystal. I introduced some of these concepts with lightning first, rather than go to the materials, because I think it makes a lot more sense to talk about the movement of charge in a bolt of lightning, something that everybody can see and understand, rather than talk about electrons moving around inside materials, which is pretty much invisible. Finally, the resistance R of a material is related to its resistivity, its cross-sectional area, and its length. Naturally, if you make a piece of material longer, the resistance is going to go up because it's harder for the battery to push electrons through it. If the cross-sectional area is increased, well, then it's easier. So that's why area is in the denominator. Because when you look at this, all these variables, there's Greek letters, a long list of terms, and what I'm always worried about is that if I go to this immediately, you might look at it and say, my goodness, look at all this mess. But in fact, the current flow in a bolt of lightning is very similar to the flow of current inside a material. And it really only depends on these 3 things: the number of charge carriers, the mobility, and the applied voltage. This is the most important slide in the entire course, so if you print out any information in hard copy, this would be the one to print. I recommend that you do that while working through the practice problems, review, and try to convince yourself that you understand what every single symbol on this slide means. Now, what's very special about silicon, and the reason why it's used so much in electronics, is because it has this very special property that if you add a few phosphorus atoms or boron atoms to it, you can dramatically change the conductivity. Let me show you. Phosphorus on the periodic table lies just to the right of silicon. It's in group 5. But otherwise, the structure and size of the atom is very similar to silicon's. It means that if I take out one of the silicon atoms from a crystal and I insert a phosphorus atom to replace it, then it'll nicely fill up all of those open valence spaces just like silicon did. But we will have 1 electron left over. Isn't that interesting? Because that electron happens to be up here in the conduction band. So for every phosphorus atom added to a silicon lattice, then we end up adding 1 electron to the conduction band of silicon. The valence band is not affected because the hole is a bound state within the phosphorus atom itself, not in the silicon crystal structure. The point I'm trying to make here is that the number of electrons in the conduction band is now different than it was before the phosphorus atom was added, but the number of holes stayed the same, right? By adding phosphorus atoms to the silicon lattice, I've increased the number of conduction electrons, but I have not changed the number of holes. By controlling the concentration of phosphorus atoms, I can thus control the conductivity. This turns out to be a very powerful type of materials engineering. All right, now let's look at the other case. What if I use boron instead of phosphorus? If I take out one of the silicon atoms and replace it with boron, which is a group 3 element, then boron will not be able to fill in all of those states in the silicon lattice. It will leave an opening or a hole that wasn't there before. And it happens to be aligned with the valence band energies of the silicon lattice. So boron can't quite fill in all the valence electron states. And that hole can move around the lattice. For every boron atom added to the silicon crystal, I've created one hole which is now free to move around, but I've not changed the number of electrons in the conduction band. Nonetheless, as I add more boron atoms, I will increase the conductivity of the crystal due to the presence of the mobile holes. This is also a very powerful way to engineer the conductivity of a material. Now, to show you the power of this method and why it's so important, I've done some simple calculations using the equation from the most important slide of the course. Now check it out. In undoped pure silicon, we have a certain hole mobility, a certain electron mobility. The same mobilities hold true whether or not you've added boron or phosphorus. The mobilities don't change. What has changed is that in the case of phosphorus, N, for example, is now increased to 10 to the 17th power per cubic centimeter, and of course in that case P would be negligible. Or in the case of boron, the hole concentration, P, might now be increased to a huge amount, whereas N in that situation would be negligible. I recommend pausing the video right now and see if you're able to calculate the resistivity of the doped silicon in each of these two cases on your own. Now, 10 to the 17th power, that might not sound like a lot, or it might sound like a lot, but silicon already has 10 to the 22 atoms. It means that we're only replacing one in every 10,000 silicon atoms with phosphorus or boron. So we're not replacing very many of these atoms. It's not going to change the way silicon looks. It's not going to change or do anything to the thermal properties or anything else, really. The only thing that's going to change is that we now have more conduction electrons in the case of the phosphorus doping, or more valence holes in the case of the boron doping. Silicon without the phosphorus atoms had a resistivity 10 to the power of 5 ohm centimeters. But when I added only 10 to the power 17 phosphorus atoms to the crystal, the conductivity dropped down to 0.042. In other words, I've changed the conductivity of the silicon by 7 orders of magnitude by just adding a tiny quantity of phosphorus. So that's the power of semiconductors. We can now modify or engineer the conductivity of a material, and we can do it in a way that doesn't really change any of the thermal properties. The lattice is still intact. If you instead doped it with boron, then the reason why the resistivity is a little higher is because the hole mobility is not quite as high as the electron mobility is. So if you have the same doping of phosphorus in a silicon wafer as you did with boron in another wafer, the N-type or phosphorus-doped silicon will be a bit more conductive. So in a semiconductor, it's a material where the conductivity can be engineered. An insulator is a material where no matter what you do to it, it's pretty much just going to stay an insulator. In a metal, it's pretty much going to stay a conductor. But you see, with silicon, we can change the conductivity very precisely by orders of magnitude. In the next video, we'll see how this property can be used to create a solar cell. But not only solar cells rely on this property, but diodes, transistors, LEDs, lasers, and everything else in the digital world rely on this conductivity modulation. I've mentioned transparency before. Let's take a quick look at diamond, silicon, and silver. Silicon's band gap is 1.17 electron volts, and it's transparent to light with wavelengths longer than 1100 nanometers. This means that silicon is transparent to infrared light, but not to visible light. Diamond, however, is transparent because visible light cannot excite one of those valence electrons into the conduction band. Visible light is not energetic enough for diamond, but it is for silicon. Silver, on the other hand, has lots and lots of open states in the conduction band. It's very easy to excite one of these electrons in silver. And obviously, silver is not transparent.